This conference will now be recorded.
Hello students, so I'm back with few numerical problems from previous year's JEE Mains paper on wave optics. So in today's class, basically I'll be concentrating on the problems from interference, basically Young's double slit experiment, okay, in short YDAC experiment, and single slit diffraction, okay, from the diffraction portion, single slit diffraction, mainly diffraction and interference. Okay, so these two topics I'll be covering, and I have in today's session only JEE Mains 2020. So I have picked up questions on these particular topics like Young's double slit experiment and single slit diffraction. As you know, I have already discussed numerical problems on the superposition of waves and very basic ideas, like questions related very basic ideas of wave optics. So today I'm going to discuss numerical problems on these two topics, and that too I'm covering JEE Mains 2020. Like that, I'll just cover the even years first, okay, because this is 2024. Somehow there is a tendency that even year means the type of the questions somewhat will come like 2020 or 2018, 2016, kind of those. So but not necessarily that, but anyway I have an intuition to have discussions on JEE Mains 2020 first, then I'll go for 2022, 2018, 16, etc. Okay, so let us complete our discussions for today. So the first question says visible light of wavelength 6000 angstrom. Okay, this is 10 to the power minus 8 centimeter. That means this is 6000 angstrom. This is actually, this light is in the orange, I think orange color. Okay, orange. Falls normally on a single slit and produces a diffraction pattern. It is found that the second order diffraction minimum is at 60 degree from the central maxima. So that means the angle theta is given for the second order. Okay, second order diffraction pattern. The first minimum is produced at, let us say this is theta 2, at theta 1. So first minimum is produced at theta 1. Then what is the value of theta 1 close to among these four options? Okay, so you know, first of all let us write for minima the condition for diffraction is a sine theta is equal to n lambda, right? So a is slit width, n is the order of the diffraction fringes. Okay, order of the diffraction minima or maxima. Here it is minima. Okay, order of the minima, like first n is equal to 1 means first order or first minima, first order minima. Okay, and n is equal to t means 2 means second order minima, like that. So here in the given problem, what are the informations given? See, theta 2 is given. So here I should write theta n. So theta 2 is given, lambda is given 6000 angstrom. This we can write 10 to the minus 10 meter. Okay, we can write this. So lambda and theta 2 is given. See, if I want to find out the angle theta, I need, see this order, I need. So here in the question you have been asked to find out theta 1 for the first order, okay. So that means n is equal to 1, you know that. Okay, lambda is the same lambda, but what is the angle, or at what angle with respect to central range the first minimum will occur. So for that you need this a, right? So what we'll do, from the given informations we'll first find out what is a. So this is the condition I am applying for second minima. Sin theta 2 is equal to 2 lambda, right? Then what will be this? A is equal to 2 lambda by sin theta 2. So what is sin theta 2? Sin theta 2 is 60 degree. So 60 degree, sin 60 degree is root 3 by 2. So 2 will come here in the numerator and root 3 like this. Okay. So what we get? We get the value of a from here. Okay, let us write this value of a somewhere. Let me erase this condition. This we know already. So a we have obtained as 4 lambda by root 3. So this we have got. Now we'll apply for the first order minima. Okay, we'll apply this condition. A sin theta 1 is equal to n means 1 here. So we'll get only lambda. So I have to find out actually sin theta 1. So lambda by a means 4 lambda and root 3 will be in the numerator. So you get this root 3 by 4. Okay. So theta 1 will be sine inverse this. Okay, so this is the value, like you have to actually guess the value, or you have to actually somehow get to know what is sine inverse root 3 by 4 is. See, root 3 by 2, anyway, root 3 by 2, sine inverse root 3 by 2 is 60 degree, right? So, and sine 30 means like a half will be sine 30. That means, you know, this is not 60 degree, that is for sure, and neither it is 30 degree. 30 degree, it is not 30 degree, so it is not 30 degree, neither it is 45 degree. So among these two, I don't know, if you have calculator access, then easily you will get this value. Otherwise you have to find out in a clever way what is the value of this. Okay, so this will be actually nearly equal to 25 degree. Okay, so better to have this in the mind, or kind of, if you can remember, because 25 degree I have been seeing questions are coming with this kind of values, which are not known to, like these are not exactly 30 degree or 45 degree or 60 degree. So sometimes these values also can come, you know. Anyway, by the way, you know that 37 and 53, you know that. Okay, similar to that, if you can adapt some process. Okay, but anyway, now I'm not going to discuss that. We can have a separate session for that. For the time being, let us go with this answer. Okay, so this is 25 degree. So the question number 2. So this is also from JEE Mains 2020. In a Young's double slit experiment, the separation between the slits, that means Young's double slit experiment, D is given 0.15 millimeter. In the experiment, a source of light of wavelength this, so wavelength 589 nanometer is used, and interference pattern is observed on a screen kept at 1.5 meter away. That means D is also given. The separation between successive bright fringes on the screen. So what does that mean? That means you have to find out the fringe width. Okay. So separation between successive bright or dark fringes is actually fringe width. Is equal to fringe width. Okay, I hope you have understood this. So beta, we know fringe width in case of Young's double slit experiment, d lambda by small d. Actually this expression for even for diffraction pattern also, minima. Okay, minima have the same expression for the fringe width, minima or secondary maxima or minima. Okay, you can just note this point. Even this is the expression for fringe width for secondary minima or maxima in single slit diffraction pattern. In case of that, you know, in place of D we write A, slit width. Okay, single slit diffraction, same formula actually. D is the separation between the slits and screen, lambda is the wavelength, this is slit width. Okay, in that place we just write A here in place of D. Anyway, so since all the informations are given, you can just find out that. So D, capital D is 1.5 meter, lambda is 589 into 10 to the power minus 9 meter divided by small d is 0.15 millimeter is 10 to the power minus 3. Now, okay, so I hope you have noted this point. I'll just erase because I don't have space. Let me make some space over here. Okay, so I have, you look here, I'll just do the simplification. So this 1.5, I'll write 15 itself so that you get here. This is 589 into 10 to the power minus 10. I hope you don't have any problem. Here in the denominator, I'll write this 10 to the power 5. So 15, 15, these are 15. I can strike them out and see what I get here. 589 into 10 to the power minus 5 meter. If I make into millimeter, if I just convert this into millimeter, see it will be 5.89 10 to the power minus 3, right? Millimeter means, yes, so 2 10 to the power minus 3, right? This is the meter, so millimeter means 589, so it is nearly equal to 5.9 millimeter. Okay, here the option C. Now let us go to the third problem. So third problem says, in a double slit experiment, a certain point on the screen, the path difference between two interfering wave is this much, 1/8 of a wavelength. What does that mean? That means delta path difference is lambda by 8 given. The ratio of intensity of light at that point to that at the center of the bright fringe. See, this is actually this question is from Young's double slit experiment. If you remember, in the double slit experiment, Young's double slit experiment, what is the intensity pattern? You know, the central maxima, all the maxima, they have same intensity actually. Okay, like this. All right. Okay, but these are actually with, you know, integral. See, these values will be having these are bright fringes. If I take this is the bright fringes, so these are n lambda. Okay, n lambda, so integral multiple of lambda. But here you look, this lambda by 8, right? We have to see this is actually, you don't have to go up to that point. Let me write the expression for the interference. Since the path difference is given, it is related to something related to phase difference. Okay, 2 pi by lambda into lambda by 8. So I get here pi by 4 is the path difference. Okay, if this is the path difference, then what will be the intensity? So we have one expression for the intensity is this: I is equal to I0 cos square delta pi by 2. I hope you remember this. Okay, I had shown you deriving this formula. This is the intensity of the central bright, and this is the intensity at particular point where two interfering wave has phase difference delta phi. So here if I put this value, see, I can just get this ratio here, I by I0, that means intensity at that point to the intensity at the central point. This is cos square phi by delta phi by 2, that means phi by 8. Okay, cos square pi by 8. So now here also, if you don't know this value, I think there will be use of calculator. So this kind of question must require use of calculator. So I'll just write the answer for you here. This will be nearly 0.853. Okay, 0.853. So this is the answer actually. All right, so this is the answer. So you have to actually the turning point here is that you have to remember this formula: I is equal to I0 cos square delta phi by 2. So this is with interference. Okay, so you know there are, I'll just tell you at the end of this class that there are particular few types of questions which are being asked in this mains exam. Okay, and okay, so as I am discussing all the questions, you can just guess the types of questions. Like you need to know the beta formula of beta, or with angular width, linear width. Okay, this is beta means linear width anyway. For the central one, for the in case of diffraction, maxima, minima. Okay, and this formula for Young's double slit experiment, etc. So these are actually the kind of typical type which are being asked in repeatedly asked in different years of this JEE Mains exam. Okay, let us go to the next point, next question. Okay, so in this question it is said, in a Young's double slit experiment 15 fringes are observed on a small portion of screen when light of wavelength is 500 nanometer is used. So now see 15 fringes are being observed in a screen. So 15 fringes are observed in a fringe like this. Suppose this is the screen, length of the screen. So length of the screen cannot be changed. Okay, once your setup is ready, you can change the wavelength of the light. So here also the thing is that you want to see 10 fringes. So it is given that when lambda 1, suppose lambda 1 was 500 nanometer, then in this screen you could see number of fringes, that means n1 is 15. Okay, now when you want to see n2 number of fringes, 10 number of fringes, what will be wavelength? Okay, on the same screen you want to see 10 fringes, so what would be the wavelength? So this is the question actually. In nanometer you have to find out, and this is actually question from section B, where you have to find out numerical values. Okay, so look here, Young's double slit experiment, we know the beta fringe width is n lambda for nth one, n lambda into d by small d. Okay, for a particular experimental setup, this and this are fixed. That means, you know, beta n, I can say beta n proportional to n lambda. Okay, so beta total, so you know I can write that the length of the screen, see I can write like this, just let me write here. So suppose 15 beta. Okay, 15 beta, 15 into beta. Okay, 15 into beta, beta means 1, just a single one, width of the single or any one of the planes is beta, say. So 15 into beta, this is equal to 10 into, suppose this is beta 1, since beta depends on lambda d lambda by d, right? So these are constant, but it depends on lambda. So the width, fringe width will be different in the second case when I am using different wavelength. But see, if I say on the same screen in the same length you want to see all those 10 fringes, then this condition must be satisfied. Okay, 15 beta 1 is equal to 10 beta 2. Now beta, will write down the expression for the beta. So d lambda 1 by small d, here 10 d lambda 2 by small d. As I said, these are common from both sides. So I have to find out lambda 2. Lambda 2 means 15 by 10 into lambda 1. So this is actually 1.5 into lambda 1. So lambda 1 is given here 500 nanometer. I am writing 500 nanometer here. That means 750 nanometer. Okay, so here it will be 750. All right, so this is the correct answer for the question. So you know, so here what you do, here you can do n1 lambda 1 is equal to n2 lambda 2. N is the number of fringes you see or want to see. See this type of pattern itself is being asked in different session of this years of question. I'll just tell you here. I'll refer this question. I think this one. You look in Young's double slit experiment. 16 fringes are observed. 16 fringes are observed in a certain segment of the screen of light of a wavelength. Okay, screen when light of a wavelength 700 nanometer is used. If the wavelength of the light is changed to 400 nanometer, the number of fringes observed in the same segment. So see how simple it is. N1 is N1 lambda 1 is equal to N2 lambda 2. So I have to find out here N2, N1 lambda 1 by lambda 2. See, N1 was 16 fringes, and then lambda 1 was 700 nanometer divided by 400 nanometer. So it will be unitless a number 4. So it will be 28 fringes. Okay, so the answer is this one. So this kind of problem was given. So this is another type of problem with Young's double slit experiment. Okay, now I'll actually, okay, I have discussed the fourth one. I'll discuss the fifth one. Orange light of wavelength this much, 6,000 angstrom. This is 6,000 into 10 to the power minus 10 meter illuminates a single slit of width 0.6 into 10 to the power minus 4 meter. The maximum possible number of diffraction minima produced on both sides of the central maxima. This is very typical question. So this is also a question from JEE Mains 2020. Okay, this is actually a typical question. So what are the informations given here? The information is lambda is given, okay, small d is given, sorry, small d means slit width. Here I have written in case of diffraction it is as small a 0.6 into 10 to the power minus 4 meter. Okay, now you have to find out maximum possible number of diffraction minima. So you know this, right? If you remember the diffraction pattern, this is central one, then first minima comes, then secondary maxima, then minima, then maxima, like that it goes, right? On either side also. Okay, like this it goes. Okay, so you have to find out how many maximum number of these minima will occur on either side of the diffraction central maxima, of the central maxima on either side of the, or on both sides of the central maxima, if these informations are given. So this kind of question we are just solving now. Before that we haven't seen, right? So let me first write the condition for the diffraction minima to occur. This you know, right? Condition for diffraction minima to occur is a sin theta is equal to a sin theta n is equal to n lambda. N is the order of the diffraction frames. See here, actually I have to find out n only, right? By lambda I have to find out n. N is the number, okay, on either side, like 1. If I just say this side, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3. Okay, so these are corresponding orders of the minima. I have to find out this maximum number of minima. Okay, maximum order, I have to find out maximum order n. So how to find out if I have to have maximum, this maximum, then look, this theta also has to be maximum. So theta has maximum value when it is 90 degree, isn't it? Theta has maximum, sin theta has maximum value when it is theta is 90 degree. See, I'll show you this figure. If you remember this figure, I'm sorry, I hope I had this. Yes, so let me, yes, so you can, I think, let me just do one thing, erase these portions from here. You know, informations are given, I am not writing again. Let me save some space. Let me bring the figure first. Okay, I have this figure. So condition, so we have to find n is equal to n lambda. So lambda by, sorry, n is equal to a sin theta by lambda, a sin theta n by lambda. See, if I have to have maximum here, so this sin theta value also has to be maximum, and that is possible when theta n is 90 degree. Look what is theta from this figure. See, this is the angle theta, the angle of deviation from the direct ray. Okay, see, this is the angle theta. See, this theta is counted from this way. Okay, this way it is counted. Now it will be 90 degree when this is the 90 degree, so it has to go like this. That means when it is infinity. Okay, look, if I want to find out maximum number, see maximum number, so let me just do one thing. Let us put this for maximum number of orders, then what we get, so n max we will get, so a is actually 0.6 into 10 to the power minus 4 divided by 6000 into 10 to the power minus 10 meters. If you do the calculation part, you will get, you will get this number is 100. But this 100 occurs where? When it is at infinity. Okay, when it goes to infinity, see, it diffracts like this. Okay, it diffracts like this, it diffracts like this, like this. Okay, and when it is infinity, okay, screen also has to be infinitely wide, and this you will see at infinity. Okay, but anyway, screen can see if I consider that I'm increasing the screen up to infinity, but still if we want to see inside the screen, then order will be at least one less. That means we are seeing that this occurs, okay, this occurs at infinity, but we want to see in the screen. On the screen, the maximum number will be 99 at least. Okay, at the most, not at least, at the most this number 99. So that is in one side. Okay, so both sides there will be this number. So I will have maximum possible number of fringes, like minima, diffraction minima, secondary minima on both side of the central maximum, and that number will be 2 into 99. Okay, 2 into 99, that means 198. You will see maximum possible number of fringes, how many, sorry, maximum possible number of minima on both side of the central maximum, that is 198. Okay, now let us go to the next problem. So this problem actually we had discussed yesterday somewhat, but I think there is some problem in the answer that we had discussed yesterday. I had myself some doubt, that's why I just come back. Today I come back with this. So look the question. In front of a diffraction by slit, if slit with A, this is not the year, I don't know in which year this question was been asked. If slit with A wavelength lambda, focal length of the lens is f, linear with the central maximum. Look, I'll refer to this figure. Maybe let me take this figure at this position. Sorry, I'm discussing this question here. All right. Sorry. I don't know what happened. Okay, I forgot to copy. Sorry. I'll copy first here, then I'll go for yes slideshow. Look here. I tried to explain somewhat yesterday. See this lens. This lens is actually for showing you this arrangement. It is being shown here just after some, see this gap is actually in the figure, it is a huge gap, but you know what is done, this lens is exactly kept at this, like just near the slit, and in fact you can consider that there is no separation between the slit and this lens. What I'm trying to mean is that this focal length and the screen is actually kept at the focus, right? So this focal length has to be considered as D. First of all, this thing you have to understand. Now the question is linear width of the central maxima. What is linear width of the central maxima? If you don't remember the formula, then you can try to remember. If you don't remember, I'll just tell you a trick. Just now we have seen beta for Y Young's double slit experiment, right? That was d lambda by d. So here we will replace the small d by a with the slit width. Okay, so this is for actually all the interference fringes, but this expression is actually for for secondary maxima or minima, right? You know that secondary minima or maxima. Why I'm saying minima or maxima? Because there are many minimum, many maximum, so that's why minima and maxima in plural form. But in case of central maximum, actually we can say, because there is only one fringe. See, central maximum will be, yesterday in the class also we had explained. See, this is the central bright one, and just after that there will be this minima. Okay, first minima will be there. Okay, so first minima will be there, like this it will go. Anyway, so my point is that we had discussed yesterday also. So the central maximum will be having with central twice of the beta of secondary maxima or minima. Okay, twice of the secondary fringes. Okay, that means, you know, 2 into d lambda by a. So this is actually a very good point to remember, that fringe width. See, if you can remember the fringe width of Young's double slit experiment. Okay, fringe width of the fringe width in the interference pattern, that is d lambda by a or d lambda by d, whatever you say. So that is actually exactly equal to the width of the secondary maxima or minima, and twice of that will be the width of the central maximum. Okay, so in this case, look, this d will be replaced by the focal length of the lens. So what is this? This is actually negligible. This separation is negligible. In fact, we can take this focal length as d, equal to d. Okay, in that case. So for that case, the width of the central maxima will be 2f lambda divided by a. Look, this C will be the correct answer. Yesterday I said this option, but it is not true. This is not correct. The correct answer and logical answer is this 2f lambda by a. Okay, I think I have discussed already the seventh one. So here I stop for today. In the next class, that means tomorrow, I will discuss about polarization of light. Polarization of light first, and then take up numerical problems from PYQ. Okay, in fact I am going to have a PYQ series, not chapter wise. I'll take general PYQ series after finishing this wave optics lectures. Okay, series of PYQ will discuss in one session. Maybe we'll discuss some 10-15 or more than that number of questions from the PYQ series. So I'll cover in the PYQ series discussions. So 2022 paper, 2020 paper, 2018 and 16 for the time being. Okay, this, I think there are 4. Okay, so this 4 I'll cover first, then I'll come up with the odds like 2021, 2023 also was over, so this I'll come up after that. Okay. Okay, so thank you for your presence. Bye for today.